Assalamu alaikum. My name is Ammar, and my colleagues are Adil, Zakaria, and Mohammed. Today, we're going to present the calculation of anode current for anode spike and current density detection in whole heroult cells. Uh, Move to the next slide. The whole heroult process, aluminum electrolysis occurs in a rectangular steel cell that is insulated with carbon, and current is supplied to it by suspended carbon anodes. The electrolyte in the pot is a mixture of cryolite, aluminum fluoride, calcium fluoride, and alumina. This mixture helps in increasing electrical conductivity of the mixture and decreases the melting point of cryolite to below 1000 degrees Celsius. Typically, cell current is from 4 to 4.5 volts, and current is 150 to 300 kiloamperes. But these values can change based on the technology being used. The aluminum formed settles at the bottom of the pot. So we move on to the next slide. The anode effect. Now, one of the problems that can happen during this process is the anode effect. It occurs when the level of alumina in the electrolytic path drops below a certain threshold value. Normal electrolysis stops at this state. The greenhouse gases called carbon tetrafluoride and hexafluorethane are evolved, and current density and voltage of the cell rise significantly, which decreases the efficiency of energy consumption. An insulating gaseous film can also form on the anode, which impedes the flow of electricity through the anode. It is important that the measures are taken before the anode effect happens. Thankfully, by measuring the voltage and individual anode current signals, we can perfect the occurrence of an anode effect. So on the next slide, we're going to talk about the effect. Just a minute. Okay. Another adverse effect is the anode spike formation. This also interferes with normal electrolysis by creating thermal and chemical imbalance and reducing current efficiency even after faulty anode is replaced with a new one. The anode spike formation has the potential to derail the entire process by weeks or even months based on its development on the anode. Again, research indicates one of the best ways to protect its development is by measurement of individual anode current signals. Now my colleague Adil will continue with the requirements.
Okay, so we have the following functionality specifications for the project. We have a very low voltage measurement range of 90 microvolts to 5 millivolts. The system needs to be able to store data and transmit it as well. It needs to be able to perform statistical analysis, and it needs to have a sort of system for detecting the formation of spikes on the anode. The working conditions are also quite challenging. It needs to work in a high magnetic field, high temperature, and high level of humidity. The dusty environment is added as a bonus, and we need to also have a system which complies with the EGA health and safety regulations. So how can we go about doing this? We have two methods. The easy way would be the voltage drop measurement, in which we will just measure a fixed length of the conductor. The current being in kiloamperes would require a magnetic field sensor. These systems are quite expensive, but they are very accurate in comparison to the voltage. So as per the proposal of the EGA, we considered two current methods, the Hall effect transducers and the magneto-optic current sensors. Firstly, we have the Hall effect. The charges are moving in a current, and they are influenced by the Lorentz force and a magnetic field. The Hall effect transducers make use of this Hall element by placing it in between a magnetic core, which is surrounding the current carrying conductor. Next, we have the Faraday effect, which is rotation in a polarized light due to the longitudinal magnetic field, and the magneto-optic current sensors make use of this. These systems are very accurate, but due to their expenses and the fact that they are finished products, not to mention the level of their complexity, we chose to go with the voltage drop method. We based our system on a reference paper, whose figure is shown here. And the top part of this figure is showing the voltage drop measuring system. And the bottom part is responsible for temperature measurement for acquiring the resistance. Then the microcontroller processes this information and calculates the current by Ohm's law, and then stores and transmits the data as required. So let's start with the temperature measurement system. The current needs the resistance measurement but this can be calculated by the surface temperature of the anode rod. The PT100 RTD sensor is an accurate choice for our system. Its accuracy is based on the 2-wire, 3-wire, or 4-wire configurations. The signal then acquired can be digitized by using the MAX 31865 chip. It's a converter which is optimized for platinum RTDs, and it's very accurate because of its 15-bit ADC. Next, we have the voltage part of the circuit. The voltage measurement starts at the amplifier. Since the voltage range is in microvolts and millivolts, we will need to amplify the signal before we start processing it. We are going to be using two amplifiers because using a single amplifier with high gain would limit the amount of bandwidth present. We'll be using a precision instrument and amplifier as our reference paper is using one, and they are also going to be using an AD8638 as a secondary amplifier because it provides low input noise and wide bandwidth, important considerations for our project. Then we have the low pass filter. The design proposed by the paper uses an active filter circuit with a cutoff at 5 Hz. This is to make sure that there are no quantization errors during the conversion at the ADC, and it also removes high frequency components and noise. They are using a third order Butterworth low pass filter with an AD8512 chip, a precision JFET amplifier. We, however, made our own a third order Butterworth filter, which has the following Bode plot, and it was confirmed that it is indeed has a cutoff frequency of 5 Hz. Moving on, Mr. Muhammad Al Masri will be presenting the next part.
What the hardware system will be the ADC or the analog to digital converter in our system to measure the voltage. Our chosen ADC was a 16-bit ADC that has 1 bit reserved for the sign of the voltage and 15 bits that can distinguish between about 32,000 different voltage levels. Our ADC of choice was the ADS1115 chip, which has a wide supply range and has a built-in programmable amplifier that can add more flexibility to our system. Moreover, this chip can also support differential voltage measurement, so we can measure the voltage with the reference of another pin, like measure it twice, one in negative 1 volt, one in positive, to remove the noise, as of just measuring it from a single end with reference to our ground. We also have made as proof of concept simulation of how our system will work. As we can see on the screen, we'll measure the voltage drop. We first we'll pass our signal to our amplifiers, which will then pass the signal to our low pass filter, which will remove the low frequencies measurements, and then it will pass it to the ADC, which is going to pass it to a microcontroller that's going to process the data, show it on a display on the device, and then also upload that data to the cloud to be processed in a database. As for our microcontroller, we choose the Arduino Uno Wi-Fi Revolution 2 because it has a built-in Wi-Fi module that's going to simplify the communication with the cloud, as we can just use the Wi-Fi signal. It's very easy to operate and program for. It's compatible with a huge library of third-party modules that are made for it, since Arduinos are open source devices. And it has a very high general flexibility as it supports different voltage levels. And it has sufficient functionality for our system. We also did an initial hardware system test where we connected our Arduino Wi-Fi Revolution 2 to an ADS and an I2C display, and we powered it using a simple 5-volt power bank. And as we can see, we can simply measure the voltage of a fresh battery, for example, and then upload it to the database where it can be processed. And now my colleague Zakaria will continue from there.
Yes, so for the data storage and transmission, we use the Google Firebase to store the data that we got so we can view it later, and for sure to store it using the Arduino Uno Revolution 2 Wi-Fi that has a built-in Wi-Fi module to communicate with the Firebase. We used initially the commands shown in the right in the slide, so to communicate with the Firebase, and so we also are planning in the future to develop a mobile app for our next part of the project that can view the data stored in the Firebase, so we can monitor our data remotely. Right now, in conclusion, yes, so the aluminum electrolysis process needs to be monitored properly in order to prevent any undesirable effects. As research has shown, individual anode current signals are very important in that regard, as they can predict these effects ahead of time. With that said, the project aims to measure the voltage and the temperature of the anode rod in order to calculate the current. But at the low voltages that we are actually measuring, accuracy and sensitivity are really huge factor for the design. So for storing data, we shall making use of the cloud storage rather than the local storage, as it is way more superior and it makes it less demanding on our prototype. There are many challenges that still remain to be resolved in terms of the adverse working condition and the impact of noise on our voltage measurements, and we are looking forward to further developing it in the capstone 2. Right now, regarding the future development, speaking of it, we have a bit more research to do and more ideas to explore. We need to do more work in evaluating the noise and its contribution to our overall system. The selection of wire so to serve as the probe of our system is also something we are looking into. The software implementation, testing, and troubleshooting is something we are prioritizing immediately, as it is the premise of our capstone 2. Due to the challenging conditions right now in which the device needs to function, we will be looking into making a finalized PCB and protective housing for the prototype. Finally, yeah, we are also planning to, and we are looking into developing a mobile or web application to monitor the process and to monitor our the values that we got remotely. So this is also something we are considering in capstone to develop. Thank you for listening.
How about if recording?